Welcome to the Fractional Calculus Seminar Series. Today we have two speakers. The first speaker is Professor Vladimir Evangelich Fedorov, born on March 01, 1972, head of Department of Mathematical Analysis, Faculty of Mathematics, Chelyabinsk State University. His education includes Chelyabinsk State University, 1994, where he received his Doctor of Physical and Mathematical Science. Since 2005. He's now a professor since 2007, honorary professor of the Chelyabinsk State University, honorary professor of Chelyabinsk State Pedagogical University, honorary worker of education of the Russian Federation, winner of the Prize for Young Scientist of International Society for Analysis, its Application and Computations, the Isaac Award for Young Scientists in 2011 for his achievements in semigroup theory and control theory. He's been an editor-in-chief of computational mathematics and modeling, deputy editor-in-chief of the Chelyabinsk Physical and Mathematical Journal, member of the editorial board of the journals, such as Bulletin of Irkutsk State University, Series Mathematics, Progress in Fractional Differentiation and Applications, International Journal of Mathematical Modeling and Numerical Optimization. We are very happy to host you here today. You may please begin your talk.
Can I start?
Yes, please.
Thank you very much. I would like to thank the organizers, respectable professors, for the possibility to take part in this excellent series of seminars. And the title of my talk is Resolving Families of Operators for Fractional Differential Equations and Banach Spaces and Applications. Firstly, I want to recall the definitions of Riemann-Liouville fractional integral and the Riemann-Liouville fractional derivative, and the Hilfer fractional derivative of this form. We know that it is interpolation in some sense of interpolation between the Gerasimov-Kaputa fractional derivative and the Riemann-Liouville fractional derivative. If beta is equal to 0, it will be Riemann-Liouville fractional derivative. If beta is equal to 1, it will be Gerasimov-Kaputa fractional derivative. As for fractional derivative of Gerasimov-Kaputa, we can define the fractional derivative, Hilfer fractional derivative, in this form. It is regularized form, and if we take here beta is equal to 1, it will be the corresponding the Gerasimov-Kaputa derivative. I will use this definition of the Gerasimov-Kaputa, of the Hilfer fractional derivative. And for negative alpha, define Riemann-Liouville fractional derivative of the order negative. It will be Riemann-Liouville fractional integral of the order minus alpha. And several words about the theory of operator semigroup. We know that this theory is about the differential equations in Banach spaces of the first order, and there are known theorems on the existence of C0 continuous semigroup of operators and analytic semigroup of operators. They are Hille Yosida theorem and Solomyak-Yosida theorem. And if we consider the differential equation with a linear closed operator, if we know the semigroup, the resolving semigroup, we will have the solution, and we can consider corresponding linear inhomogeneous equation, and the resolving semigroup take part in the construction of the solution of such equation under certain conditions on the function phi in the right-hand side. And if we use such results about the linear inhomogeneous equations, we can consider a semi-linear equation. And by this formula, we will have equality equation for a solution in the form of this integral equation, and using fixed point theorem in the appropriate space, we can obtain the unique solvability of the Cauchy problem for the semi-linear equation. Analogously, for differential equations with fractional derivatives, let it be d alpha, some fractional derivative. And if we have no resolving semigroup, because the semigroup property is a characteristic property for the first order equation, but we will have a resolving family of operators, and if we have such family, we will construct the equation of the arbitrary initial value problem for our equation, and we can study linear inhomogeneous equation under some conditions on the function f, and we will obtain this form of the solution of the Cauchy problem for such equation, and we can consider quasi-linear equation with fractional derivatives, where d alpha is the oldest derivative, alpha is greater than alpha 1, alpha 2, and so on, alpha n. And we will obtain equality for the solution of initial problem for such equation, and considering the right-hand side of this equality as an operator is especially chosen function space, we can obtain the results on unique solvability of initial value problems for quasi-linear equations. So if we have a resolving family of operators for equation of fractional order, we have no semigroup, but we have a family of operators which allows us to represent the solution of the problem or prove the existence of such solution in the nonlinear case. Several words about famous books of Hille, Phillips, and Yosida on the semigroups theory, and the work of Salomyak on the generation of analytic semigroup of operators, the work of Daprat and Iannelli about resolving families of linear integral differential equations in Banach spaces, the famous monograph of Jan Pruss about the resolving families of evolutionary integral equations and applications, and the known work of Emilia Bazhlekova on fractional evolution equations in Banach spaces and its resolving families. Firstly, I will consider an example. It is a result of Emilia Bazhlekova. We will consider the Cauchy problem for the equation with the Gerasimov-Caputo fractional derivative, and a family of operators, of linear bounded operators in a Banach space Z, is the resolving family of operators for equation, just a moment, for equation 7, if there exists k and omega such that this inequality is valid, it is exponential boundedness. The family of operators is strongly continuous, and in 0 point, it will be identical operator. Operators ST commute with operator A, and for every Z0, such function is a solution of this Cauchy problem for equation 7. Here, the first initial value is non-zero, and other values are zero in the statement of the problem. And if we have a resolving family of operators, then a solution of problem with arbitrary values in the Cauchy conditions has such form where J, K are Riemann-Liouville integrals of the order K. And operator, a linear closed operator and densely defined in the Banach space is called the operator of the class C alpha G omega for some constant, non-negative constant omega, if the following two conditions are fulfilled. For lambda from the right half plane in the complex plane, alpha power of lambda, principal branch of this function, power function, alpha power of this number belongs to the resolving set of operator A. And there exists K such that for all lambda from the right half plane and for all natural numbers, these inequalities are valid. We see this definition we can find in the work of Emilia Bajlekova. We see that if alpha is equal to 1, then these conditions are the Hille Yosida conditions. And the corresponding result, there exists a resolving family of operators for equation 7 if and only if operator A belongs to the class C alpha G omega with some omega. And we can consider such theorem as generalization in some sense of the Hille Yosida condition on the generation of C0 continuous semigroup of operators. I want to consider analogous problem, but for the Hilfer fractional derivative in the equation. We will consider the Cauchy type problem of this form for equation 9. The Cauchy type problem in terms of maybe monograph of Kilbas, it is the Cauchy problem, but not for the function of solution, but for its fractional derivative of this order. A family of operators, linear and bounded operators, is called resolving for equation 9 if the next conditions are satisfied. There exists constant k omega such that this inequality is true, and we see here exponential boundedness and a singularity, power singularity at 0 point. Since we consider not Cauchy problem, but Cauchy type problem. The family of operators, this family is strongly continuous for positive t, and this strong limit is equal to identical operator. Operators ST commute with operator A. ST Z0 is the solution of the Cauchy type problem where the first initial value is arbitrary from the domain of operator A, and other values are 0. Here I used the notion of a solution of the Cauchy type problem. I use the classical solution. Here we have the definition of such solution, a function that from the semi-interval continuous in the norm in the graph norm of operator A is called the solution of the initial value problem 10 to equation 9 if this fractional integral is m-1 times continuously differentiable on the segment, and the Hilfer fractional derivative is continuous on this semi-interval. Equality 9 is valid for all t, and conditions 10 are satisfied. Note that for the case of linear bounded operator A, the resolving family of operators for equation has the form of Mehta-Leffler function, this Mehta-Leffler function. So the case of the bounded operator is not interesting because this operator function we know very good, and it is a series which converges in the norm, in the operator norm. The definition of a class of operators: an operator A is called the operator of the class C alpha beta omega for some constant, non-negative constant omega, if the following two conditions are fulfilled. For lambda from the right half plane, alpha power of such lambda belongs to the resolving set of operator A, and there exists K and such that for all lambda from the right half plane and for all natural n, these inequalities are valid. So we see that if beta is equal to 1, we will obtain the definition of the class C alpha G. It is C alpha G is C alpha 1. And we can consider that for every beta from the segment 0, 1, this class is a subset of the class C alpha 1. And one important property of the class of such operators, if A belongs to the class C alpha beta omega for alpha greater than 2, then operator A is bounded. Such result for the class of C alpha G was obtained in the work of Emilia Bajlekova, and here we see analogous result. So the case of alpha greater than 2 also is not interesting. We will consider only alpha from the semi-interval from 0 to. And the main aim of the first part of my talk is formulate the result on sufficient and necessary conditions for the existence of resolving family of equation 9 with the Hilfer fractional derivative. And it is known in such problems, starting from the case of the semi-group of operators when alpha is equal to 1, that one implication in such assertion is simple. If there exists a resolving family of operators, then it can be shown easy that operator A belongs to the corresponding class, and here the situation is the same. If there exists the resolving family of equation 9, then operator A belongs to this class C alpha beta omega. But the inverse implication is very difficult, and it is difficult is in the theory of semigroup theory. It is difficult in the theory of fractional differential equations, because such function have to be a Laplace transform of the resolving family if this family there exists. But we do not know about this. We have no resolving family. So, but we cannot have the inverse Laplace transform for this function. In general case, it may be that there is no such inverse Laplace transform, and we will use the Phillips inversion formula for the inverse Laplace transform, and we will construct operators S and T of they are such series which are convergent in the sense of operator norm, and we can show that the norms of these operators satisfy such inequality. And so we see the exponential boundedness and a singularity, power singularity at 0 point. And main result has such form. Let alpha is from 0, 2, beta from the segment 0, 1. Then there exists a resolving family of operators for equation 9, if and only if operator A belongs to the class C alpha beta. In this case, resolving family, the operators of resolving family are strong limits of these approximations, these Phillips approximations, which were considered on the previous page. And the main part of the proof of this theorem is to show that such strong limits there exist, and to check all the points of the definition of the resolving family for equation 9 for such operators. And so for operators from such class, C alpha beta, and only for such operators, there exists a resolving family of operators 9. We know that the existence of resolving family in some sense is equivalent to the well-posedness of the initial value problem. And now we can formulate corollary from the main theorem. If operator A belongs to the class, this class, then for alpha from the semi-interval 0, 1 for every initial value, Z0, there exists a unique solution of the Cauchy type problem of this form for equation 9. The solution has this form. And for alpha from semi-interval 1, 2, for arbitrary Z0, Z1 from the domain of operator A, there exists a unique solution of the Cauchy type problem for equation 9, and the solution has such form. And I said that the existence of resolving families is important for the study of the fractional differential equations, but it will be to have analytic resolving families. They have very good properties which are convenient for the work in applications. We will consider now analogous results on the sufficient and necessary conditions on the existence of analytic resolving family for equation 9. Denote by S theta omega such sector in the top of omega with angle of 2 theta, and another sector sigma psi in the top of 0 with the angle to psi. A resolving family of operators is called analytic if it is extendable analytically on a sector sigma psi 0 for some psi 0 with this interval, semi-interval. An analytic resolving family has a type psi 0 omega 0 delta for some psi 0 omega 0 delta if these parameters psi 0 will be the angle of the sector of analyticity of this family. Omega 0 will be at the top of this sector. And delta is the parameter of power singularity in 0 point. So there exists C such that for all t, the inequality is valid. Here we see what the sense of the parameter delta. Denote a class A alpha theta omega theta 0 omega 0 for some theta 0 from this interval omega 0 non-negative as a set of all linear closed densely defined operators in the Banach space, such that for every lambda from some sector we have that alpha power of lambda belongs to resolving set of operator A. For any theta less than theta 0 but greater than pi divided by 2, and for any omega greater than omega 0, there exists k such that for all lambda from such sector, we have this inequality. And we see that the first condition is more restrictive than analogous condition in the definition of the class C alpha beta, because this sector is wider than half plane. This sector contains half plane and it is wider. But the inequality, we have no sequence of inequalities, and as in the definition of class C alpha beta, we have only one inequality. It is very convenient in the work with applications, and it is known that every operator from class A alpha will belong to the class C alpha beta. And we will define A alpha without parameters as a unification of A alpha with theta 0 omega 0 for all theta 0 and omega 0. And the theorem let alpha beta as before. Then there exists an analytic resolving family of such type for equation 9 if and only if operator A belong to the class A alpha. Operators from the resolving family has such form, and here we see the integral over this contour, which goes to the left in the complex plane. So by the properties of the exponential function, this integral will be convergent for every power of lambda if t is greater than 1. And such integrals can have some troubles only in the case of t is equal to 0. And we see that here, as an operator of resolving family, we have very convenient integral, but not approximations for every operator, as in the case of the previous, of the strongly continuous resolving families. And such theorem can be called as generalization of the Hille Yosida theorem, because in the case of alpha is equal to 1, we will obtain analytic semigroups of operators, and it will be theorem on the necessary and sufficient conditions for the generation of the analytic semigroup of operator, on the generator of analytic semigroup. And for Gerasimov-Kapluta derivative, such result was obtained by Emilia Bazlekova. And I will not prove this theorem, but I note that the proof of this theorem is based on these results, Savat type theorem. If delta is equal to 0, it will be Miroslav-Savat theorem. This theorem is about necessary and sufficient conditions on the Laplace transform of a function which is analytic in a sector and satisfies such inequality with exponential boundedness and the singularity in 0 point. And now we can consider linear homogeneous equation with Hilfer fractional derivative. And in the theory of semigroups, it is known that classical solution of the Cauchy problem for such theorem exists in 2 cases. If function f is continuous in graph norm of the operator A, or if function f is Hölder continuous in the norm of all the Banach space. And now we will obtain analogous result. So we define a solution of the Cauchy type problem for equation 11 as before. Denote such operators as these integrals, and contour gamma is the same as on the one of previous pages. And such theorem, if operator A belongs to the class A alpha, initial data Z0, Z1, and so on, Zm-1 belong to a domain of the operator A, and function f is continuous in the graph norm of operator A, or Hölder continuous in the norm of the Banach space Z. Then this function is a unique solution of problem 11-12. In other words, this convolution is a solution of equation 11 with 0 initial conditions. And for the case of for the class of operators A alpha, we can obtain the perturbation theorem. Such theorem was proved by Cato in this monograph, and here we have analogous result. If operator A belong to this class and B operator which is which has such property, domain of B wider than domain of A, wider or equal, and this inequality 13 is valid with such constants gamma and q from this interval 0, 1 satisfies this inequality for all theta and omega, then the sum of two operators A and B belong to the class A alpha also, but with greater, generally speaking, greater parameter omega 1. If operator B is linear and bounded, then inequality 13 is fulfilled with gamma is equal to 0 and delta is equal to the normal operator B. So the sum of operator from the class A alpha and the bounded operator will belong to the class A alpha also. We will consider an example, a qualitative example in the space of sequences L2. It is the space of sequences for which such series converges, and for alpha from 0, 1, beta from the segment 0, 1, gamma from the semi-interval -2, 2, consider the Cauchy problem. We will consider this problem as our abstract problem 9, 10 in the space Z, which is equal to L2. Operator A gamma will be operator of the multiplication of every component Zn of the sequence by the number n exponential function of I pi gamma divided by 2. And so the domain of this operator are such sequences from L2 such that this sequence is from L2 also. And it is easy to show that the spectrum of such operator is this sequence of these numbers of multiplying. And for gamma from the interval minus alpha alpha, the spectrum intersects with the alpha power of the right half plane for every omega greater than 0. So A gamma cannot belong to the class C alpha beta. The first condition of this class will not be satisfied. And for gamma from this set, we can use for every n such problem as the scalar problem, and then we will obtain solutions in the form of this Mehta-Leffler function. And the sequence of such functions will be resolving family of operators. It can be checked, and we can excuse me, we can use the asymptotic formula for the Mehta-Leffler function, and we see that n in negative, we have a negative power of n. So as gamma is linear bounded operator on LT for every t. And therefore, A gamma will be from the class C alpha beta. It can be checked all the points of the definition. But if gamma is equal to alpha, then we will have n with positive power, generally speaking, positive, except in cases beta is equal to 1 or alpha is equal to 1. When this power is positive, operators S alpha t are not bounded. So A alpha are not from the class C alpha beta. If beta is equal, if beta from this semi-interval and alpha from this interval. But if beta is equal to 1 or alpha is equal to 1, then we will obtain bounded operators, and we will obtain resolving families, and we will obtain operators from the class. And in the case of beta is equal to 1, we will have the problem with the Gerasimov-Caputo derivative. And so this family of operators will be resolving for such equation. And if and alpha will be from the class C alpha G. And if alpha is equal to 1, then we will have the first order equation, and we will have a resolving semigroup of operators of this form. It will be semigroup. Moreover, we can note that in the case on the previous page, when gamma from these two intervals, we will obtain analytic resolving families, not only strongly continuous, but also analytic. And so operators A gamma will be from the class A alpha. But in this case, when we have such resolving families, and they will not be analytic, and the operators will not be from the class L alpha. It can be shown. Now we will consider an equation which can be interpreted as equation of ultra slow dynamics of non-relativistic systems. Here we have Hilfer fractional derivative in the equation and Laplace operator multiplied by imagery unit. This is 17 is a boundary condition. In we have a problem in a bounded domain with a smooth boundary, and 18 is initial conditions, and we can choose that Lebesgue space operator A will be the Laplace operator multiplied by I. dA is a Lebesgue Sobolev space with zero trace on the boundary, and we have the spectrum of this operator. It is known if we take functions Zn t as Fourier coefficient with respect to the eigenfunctions of the Laplace operator, then this problem 1618 can be rewritten as this problem, and therefore operator A will be in terms of that problem operator A minus 1, and it will be from the class of C alpha beta for alpha not greater than 1. Moreover, it will be from the class A alpha for alpha less than 1, and this operator will not be from class C alpha beta for alpha greater than 1. Another application, excuse me, how much time I can use now?
5 to 10 minutes. Then we have to go to for question and questions.
Okay, I will be briefly. And we have application to linearized fractional Boussinesq system. This problem has initial conditions, boundary conditions, and two equations with time derivative of the fractional order, Hilfer fractional derivative, and this equality is the incompressibility equation. and we will use we will choose special functions. Unknown functions here are the vector function of velocity and the vector function of pressure gradient and the temperature function, scalar function of temperature. And we will take such spaces of powers of Lebesgue space and Sobolev space, and the subspace of solenoid functions in the corresponding norm will be denoted by H sigma or H sigma 1. HP will be the orthogonal complement for H sigma and in L2, and sigma and P are respective orthoprojectors. It is known that this operator in the space of vector functions L2 and with the domain H sigma 2, this domain, this operator was studied in the book of Ladizhinskaya. It is vector Laplace operator, and it was shown that this operator has analogous properties to the properties of usual Laplace operator. And here we see we will take lambda k eigenvalues of such operator and phi k respective eigenfunctions. And the usual Laplace operator will be A2 with the eigenvalues mu k and eigenfunctions psi k. And we will need two operators, E3 and P3. E3 will be operator which every scalar function maps into such vector function. And P3 will be operator which every vector function maps into this third component. And we will act on equation 21 by the projection sigma. Just a moment. This equation 21, and here we see pressure gradient, but it is known that pressure gradient is potential vector function, and such functions are in the kernel of the projector sigma. So we will obtain this equation, and if we will find equation V, then we can get pressure gradient from the equation 22. Therefore, it is sufficient to consider system of equations 22, 24. It is 24 instead of 21. Taking into account the incompressibility equation 22, we put Banach space Z will be such a product, and the operator A will be matrix of operators with such domain. We can prove that operator A belongs to the class A alpha in the conditions of this problem. Here we have the proof of this fact. We can find this operator. We will use operators T mu, V mu, and then we can obtain the inverse operator. And after that, we need to check the validness of inequalities of such form for every element of this matrix. And after that, we will obtain this result, and operator A will be from the class A alpha. And using this fact and the theorem on unique solvability of linear homogeneous equation, we will obtain such theorem on the unique solvabilities of problem 19, 20, 24, 22, 24. And in the case of alpha from 0, 1, analogous result can be got for problem 20, 22, 24 with the initial conditions of this form. And several words about the works on this topic. The first part about strongly continuous resolving families was obtained in this article. The result on the analytic resolving families of the equation with Hilfer derivative was researched here. These two works are about strongly continuous resolving families for equations with other derivatives. Here we see several works on the equations with the Dzhrbashyan-Nersesyan derivative. I note that Hilfer derivative is a particular case of the Dzhrbashyan-Nersesyan derivative, and every finite composition of Gerasimov, Caputo, and Riemann Liouville derivatives can be represented as one Dzhrbashyan-Nersesyan derivative. And here works about the equation with distributed derivatives, fractional distributed derivatives of Gerasimov, Caputo, and in the case of Riemann Liouville, the problem has very exotic initial value problems. Several works about the multi-term fractional derivatives with Riemann Liouville derivatives, and it is known, it was proved that the Cauchy type problem has a defect, so-called defect. It is a number of the Younger initial conditions which must be zero for this solvability of the problem. And several works about quasi-linear equations. Thank you very much.
Thank you very much for the nice talk. For questions, please raise your hand and I will call out your name as they appear on my screen. Okay, I don't see any raised hand. I have a question. So for equation 21, the fractional Boussinesq equation. So how did you construct this equation?
Once again, please, what?
So the equation number 21.
Yes.
So, okay.
And
so
I substitute instead of 21 the equation 24 without the pressure gradient.
Okay.
And if I will know the velocity vector function, then I will find the pressure gradient through this equation 21. It is approach will be this approach was used in the book of Ladizhenskaya, mathematical
I see.
hydrodynamics issues. Yeah. And in this book, it was done so, and it is not my idea.
Yes. I'm acquainted with the with that level of idea. In the discrete case, they have Chorin's projection where exactly they do the similar idea where they get rid of the pressure gradient as well. So anyway, my question was on like, okay, the construction of equation 21. So fractional Boussinesq system. So how did you construct? How did you construct this equation? What is the thought process behind this construction?
How did you, one word next, how did you what?
Construct this equation. So I see.
Construct. Okay. I take usual Boussinesq system, and it is a modification of the Boussinesq system, classical. And I consider not first order time derivative, but Hilfer fractional derivative. And the right-hand side of the system is a linearization in 0 point of the natural Boussinesque system.
I see, I see. So because to my knowledge, Jacques Lyons had a similar fractionalization of it. So what he does is takes the Navier-Stokes equation and then he substitutes with the fractional Laplacian in the diffusion term. So so I want to understand, why did you consider time as opposed to space, the time derivative rather than the diffusion term?
Excuse me, I am here badly.
Yeah, okay.
Now.
I'll repeat. I'm sorry. So what Jacques Lyons did was take the Navier-Stokes equation in the diffusion term. He replaces with a fractional diffusion term, and that's what he calls fractional Navier-Stokes. So I want to understand, why do you consider time as opposed to space? I mean the diffusion term, fractionalizing it.
Can you write it?
Okay.
The question.
Okay. Okay.
Excuse me. Is it finished?
Yes, yes. Sorry. Uh,
Okay.
so I quickly typed up something. Yeah.
One time I said that it is modified equation. For example, I saw many equations where such change the first time by the fractional time derivative leads to the modeling of such effects. For example, in the in the problems with anomal diffusion, for example. And here it was done not in the it was done as for considering my methods for such not very simple system, but not from the it was not from such applied problem,
I see.
only
I
for
see.
the considering of the method, for illustrating of results.
Mm-hmm. I see. I see. I see. Because this was interesting, because when I started deriving these equations from first principles, I had a fractional in time operator, or also a fractional in space operator. So this was my curiosity. And secondly, then the incompressibility condition, it was not divergence of velocity equal to zero. In this case, in my case, it was the fractional divergence of velocity equal to zero. So very happy to see that part. But yeah, but in my equations, but there is not much work, so um, yes, please. somebody has a question. Yes, please. Professor Kerbel, go ahead.
Professor Vladimir, thank you for this nice and interesting subject on operator resolving families for fractional differential equation. But I have just it's not really a question, but clarification, because I want to see the comparison between Hille Yosida Phillips for classical derivative and the one you had for Hilfer fractional derivative. You are saying that no resolving semi-group operator for fractional differential equation. So compared to the classical Hille Yosida Phillips, can you please explain why this is not satisfied here?
Okay, I will try. When we consider the first order equation, we have resolving semigroups of operators, and we have a generator of such semigroup.
Yes.
And this generator is operator A in a linear equation, but it can be defined as operator by the definition of usual first order equation, the definition of generator. But here we didn't use the notion of generator of the resolving family. We also consider the equation, and the operators, resolving operators, has the same sense as for first order equation. They are operators, for example, operator ST is a mapping from the initial value of the problem into the value of the solution at time t, and the same sense of such operators, and this theory is very useful for the considering of linear homogeneous, linear inhomogeneous, and even quasi-linear equations and initial value problems for such equations. And I want to say about it. But we have no semigroup property, but nevertheless, it is very useful tool for study of equations, resolving family of operators.
Okay, so that's the reason why we express the solution in the integral form in terms of family rather than semigroup, right?
We represent the solution in terms of resolving family of operators.
Yeah.
For fractional differential equations. In many cases, such operators can be constructed explicitly, and the formula for the solution can be obtained explicit formula.
Thank you so much.
Okay, do we have any final questions or remarks before we close? You can unmute your mic. Okay, I assume no. So we close the talk here. Again, we thank Professor Fedorov for this nice talk. It was very nice having you here today.
Thank you very much.